Hi, my name is Annette and this is Chemistry at Glance. In this video, we're going to practice past paper questions on volumes of gases, ideal gas equation, and the mass spectrometer. If you're not familiar with this topic, please visit my blog first, where I explain everything you have to know and everything I learned for my exams when I was at A-levels. So let's start with the first question. Hannah is asked to measure the rate of reaction of calcium carbonate with dilute hydrochloric acid. She is given 1.50 grams of the carbonate and 20.0 centimeters cubed of hydrogen chloride of concentration 1.20 mole decimeters minus 3. This is the equation. And now we're asked to calculate the number of moles of hydrochloric acid used in this reaction. In order to do this, we need our equation. We know the concentration of hydrochloric acid, 1.2 moles. We know the volume, which is 20 centimeters cubed. So all you gotta do is put it in, 1.2. But remember, we have to change our 20 centimeters cubed to decimeters cubed, which is thus times and by 10 to minus 3. Put it in a calculator, and the answer you get is 0.024 moles. Part B. Calculate the minimum mass of calcium carbonate. This is calcium carbonate. Needed to react completely with this amount of acid. So this amount of acid has to react completely, so all of it. So firstly, we find the ratio between them two. It's 1 to 2. 2 moles of hydrogen chloride needs 1 mole of calcium carbonate. So our 0.024, which is the moles of hydrogen chloride, we have to divide by 2, which gives you 0.012, and this is in the moles of calcium carbonate now. And we have to find the minimum mass of calcium carbonate. In order to find mass, we use this equation. We rearrange it to find M 0.012 times our M of calcium carbonate, which is 40.1 plus 12 plus 16 times 3. And our final answer is 1.2012 grams. So this is the minimal mass of calcium carbonate that needs to be present to completely react with hydrogen chloride. Now, we asked to calculate the volume of carbon dioxide formed at 25 degrees Celsius. And we also told that 1 mole of carbon dioxide occupies 24 decimeters cubed at 25 degrees Celsius. So for this part, we're actually going to need this equation. If you're not familiar with this equation, please visit my blog. Leave all the links in the description box below, where we go through all of these equations that you have to know off by heart for the exam. So you want to find the volume, so we want to rearrange this equation. We also know that the number of moles of calcium carbonate was 0.012, and this is a 1-to-1 ratio with carbon dioxide, so the N will be still 0.012. And what we also know is that at 25 degrees, which is what we have, the Vm, so the standard volume, is 24 decimeters cubed. So we don't have to change from centimeters to decimeters because it's already in decimeters. And the answer for this is 0.288 decimeters cubed. So this is the amount of carbon dioxide that was formed. We use this equation when we don't actually get a concentration. In order to use this equation, you can use this one. This you would always get in a question, or it's at the beginning of the data booklet. Next part, calculate the volume of carbon dioxide that would be produced at 50 degrees, assuming that the pressure remains unchanged. So for this, because carbon dioxide is a gas, we can actually use our ideal gas equation, which is PV equals nRT. This is another equation that you gotta remember. I know there's a lot of remembering, but if you practice these questions a lot and you write these equations a lot, they actually stick in your mind and you don't even realize when they do. So what you said is that pressure remains unchanged. So it's going to be constant, so we can actually cross it out. We also know that R is a constant. Therefore, what we actually want... Oh, and our N will be the same because it's a one... Both of them, carbon dioxide, both will have the same amount of moles because it's the same. We just have them at different temperatures. So what we actually got is... Do you know what? I'll actually show you a different way so that you know what's going on. So we want to compare two different temperatures. So we can rearrange this equation so that we're comparing. So PV over nRT, if we take this down, would equal another PV over nRT. Because we're comparing, so you can compare these two equations as well. But as I said before, pressure will be unchanged, N will be unchanged, and R is a constant. So what you actually got is V over T, but comparing at different temperatures. So we know the V at 25 degrees, because we just calculated it, 0.288 decimeters cubed. We also know the temperature, 25 degrees. But remember, for the ideal gas equation, we need the temperature in kelvins. 25 degrees in kelvins is 298. It's 27.3 is the 0 kelvins plus, and the 25 equals 298. And that's equal to V2, which we don't know, over the other temperature, which we're comparing. It's 50 degrees Celsius, so 323 kelvins. It's in decimeters cubed, but for this type of equation, we need in meters cubed, so we times it by 10 to the minus 3. So, when we've got all of the numbers already put in, you want to find V2. So you do 0.288 times 10 to the minus 3 over 298, then take this over, so times 323. So V2 is actually 3.12 times 10 to the minus 4 meters cubed. And this is your answer. And next question. Sodium nitrate decomposes on heating, as shown by the equation. When a sample was decomposed completely, the oxygen occupied a volume of 700 centimeters cubed at a pressure of 101 kilopascals and a temperature of 28 degrees Celsius. Calculate the amount in moles of oxygen produced. So, when you see a gas constant, and temperatures, and pressures, and volumes involved, you straight away should think ideal gas equation, which is this. This time we're going to use a whole equation because we want to find number of moles of oxygen. So pressure in this equation has to be in pascals. We've got 101 kilopascals, which will be 101 times 10 to the 3 pascals. Next, volume. We've got 700 centimeters cubed, but we need this in meters cubed. So we do 700 times 10 minus 6 meters cubed. The transitions from centimeters to meters, you all got this in the data booklet. It's times 10 to the minus 6. So don't worry about this. Next thing, and we're trying to find R we got is the constant, and temperature is 28 degrees Celsius in here. We need this in kelvins, and this would be 273 plus 28. And this gives you 301 kelvins. So now you want to rearrange this equation to find N. PV over the RT, take this bit over, equals N. Pressure, 101 times 10 to the 3. Just put in the numbers now. 700 times 10 minus 6 over R, which is 8.31, our constant, times temperature, 301 equals N. So nothing easier, just put this in the calculator and you get 0.0283 moles. Remember not to make mistakes when writing this down. Try to write it if you have time in the exam. Try to write it twice in your calculator to make sure the answer you get is correct. The mass spectrum of naturally occurring sample of potassium gave the following results. Isotope and abundance. These results can be used to determine the relative atomic mass of potassium sample. Complete the following definition of relative atomic mass. So this question is all about the mass spectrometer. So our relative atomic mass of an element is the average mass of one atom of the element relative to, and our constant explanation is 1/12 the mass of one atom of carbon 12. I hope this definition sticks in your mind by now. If it's still not, keep writing it, and it will you'll wake up and you'll straight away think of this definition if someone tells you relative atomic mass. But actually now, doing a mass spectrometer question, it's calculate the relative atomic mass of the sample, giving your answer to full significant figures. So, from these results, we can actually calculate the AR. And the equation to do this is the isotope number times abundance plus same thing, depending on how many isotopes you've got, over the total abundance. So for this example, it's going to be 39 times 93.26 plus 40 times 0.012 plus 41 times 6.730 over the total abundance, which is 93.26 plus 0.012 plus 6.730. Put it all in a calculator. You don't have to worry about working it out. You can just put it in a calculator and it will do it for you. And the answer you get is 39.13. If you want to make sure it is correctly, you can check it with your periodic table. What you want to do is find potassium, 39.1. This is the relative atomic mass for potassium. From our calculation, we got 39.13, which is 39.1. So we did it correctly. Second part of this question says, this spectrum was produced by potassium ions in a mass spectrometer. State why a vacuum is needed inside the apparatus. So inside the mass spectrometer, we've got a vacuum. This is because in spectrometer, the particles are accelerated to a particular amount of energy. So they all fly with the same kinetic energy. If we had air particles in it as well, they would slow down our positive ions that we just accelerated. Therefore, vacuum is used so that we have no air particles is used. So no air particles slow down the positive ions. If you want to see how a mass spectrometer works and how it looks inside, please visit my blog and I show you everything in there. So now we've got our last question. A sample of water containing 1H2, 16O and 2H2O was analysed in a mass spectrometer. The trace showed a number of peaks. Suggest which ions are responsible for the peaks at mass number 2, 18 and 20. So at the mass number of 2, we had 2H plus ions. It could be this, because this is the elements that were present, or the compound, the molecules, but they are then transferred to ions. So H2 will actually have H plus ions, but we've got 2 of them to give us a mass number of 2. So the next one is 18. So the mass number of 18 could be our water, because 2 hydrogens, 2 plus 16 is 18. But it has to be actually just one water, not 2. And you also remember about the brackets and the pluses, because it shows you that, it shows the examiner that you know it's ions and it's positive ions. And the last one is at mass number 20. So at mass number 20, you would basically have this with the oxygen. So 2 H2O pluses. And next part. On Earth, iodine occurs as only one stable isotope, 127I. Using your understanding of the mass spectrum of chlorine, sketch and label the mass spectrum of a sample of iodine. So what you want to do first is draw a graph. On this axis, you have the MZ. On this axis, you have the relative abundance. So we're told actually that iodine has an isotope at 127. So let's write 127, and this is our iodine. From the chlorine spectrum, we know that chlorine has actually 2 isotopes, and they combine differently to create another peaks. Iodine only has 1 isotope on Earth. This means that when it combines with another isotope, it has another peak at 254, which is 2 times this. You don't worry about the height, because they won't mark you on the height. If there were more isotopes, they would combine differently. Like chlorine has a 35 chlorine isotope and 37 chlorine. So they can combine like this. They can combine like this. Or they can combine like this. Or like this. There are different combinations because this has 35 and 37, so they can combine differently. With iodine, we only got this, because there's only 1 isotope. And the last bit, a sample of iodine extracted from a meteorite was found to have a relative atomic mass of 128.7. State what this tells you about the composition of the iodine within the meteorite. So this is different than this one. So than the isotope found on Earth, because it's not Earth anymore. It's meteorite now. This shows us that iron has actually an isotope. With higher MC, which is the mass number, than the stable 127 found on Earth. So this shows us that iodine actually is stable at another atomic mass, but it's just not on Earth, it's on the meteoroid, so in space. These were the questions. Remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I leave all the links in the description box below with the links to my post as well if you want to know something more about the mass spectrum or like see how I learned it. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Thank you. Like, subscribe, and see you soon. Bye.